Hello and welcome to my presentation about hurdles of testing large-scale software systems. My name is Michaela Greiler, and if you want to write me an email, you can just send it to hi@michaelagreiler.com. You can also find me on Twitter. Well, so the story that I want to tell you today is a story or a project that happened when I was working at Microsoft Research in Cambridge. So at that time, we were asked to look at the testing practices of some of the product teams. In particular, we were looking at testing practices for Windows and for Office, and then several others came, for example, Dynamics, which I will talk today about as well. So what was our challenge? What was our problem? What was the investigation that we should lead? Well, we were looking at how can we increase the release cycles, the frequency of the releases. How can we shorten the release cycles and make more rapid releases possible by decreasing the testing times of product teams inside Microsoft? And so when we were confronted with this question, with this ask, we were really starting at the very beginning with a very fundamental question, and that was, well, why are we actually testing our software? Why do we test? And I would have loved to ask you today, but it's a little bit tricky. And so I asked people on Twitter, why do you test your software system? And I got a lot of responses. A lot of people wanted to tell me about why they are testing. And I think quite a few of the Ministry of Testing people were part of that. And so I want to tell you some of the reasons that people told me why they are testing. Some people said, because it lets me sleep at night. Another person said, because I want to mitigate the risk. Another person was telling me, well, I'm testing because it's hard or it's not seamless to translate business into logic. A lot of people were talking about customers and how they don't want that the customer tests for them, so they test. Or they were telling me about their perceptions and their thoughts about the system and how testing helped them to understand whether or not their perception of the system was actually happening. A lot of people told me also about errors, that humans make errors or they make errors, and that things are not bug free, and so we are testing to find those bugs or make the system better. But so there were a lot of different answers. And some of them were like proxy measures, like it lets me sleep better. Well, why is that actually happening? And if we boil it down, I think there are two very fundamental things. There are other things, but two very fundamental things. And this is testing helps us to find defects, and testing increases our confidence about the software systems. It increases that if the test pass, we think, well, that's good, right? There's probably no problem. And it increases our confidence that if we make changes to the system, if we make errors, we will find them. So those very fundamental things, I think, distilled or could be distilled in almost all of the answers. And now say you're running your test suite and all tests are passing. How do you feel? I guess you're feeling something like this. You're feeling like, yay, that's awesome. At least I feel like this. Everything is green. I'm awesome. This worked. There is no error. Wonderful. We can move on, right? And so a passing test is a very positive event. It's like, yes. And here's one of those tests, right? A passing test. And we are happy. And then more tests are passing. Well, so we are having a good week. We are having good 10 days. Well, we are on a roll. And then you're having a good month. And then we're having maybe even longer time. A good time. And now the question becomes, are we still happy about that? All tests are passing all the time. Maybe we are not that happy. Maybe we are not in this state of, yes, this is a good sign. Maybe you're more in this state like, something seems off here. And so why is that? Well, let's think back about what we said. What's the value of a test? Well, finding defects. Apparently we are not finding any defects. And increasing our confidence. So now we could say, well, we are superheroes. We are so great that for days and weeks on a row, nothing failed. Apparently we don't make any errors. But I think we might know that that's not completely true. So maybe the more tests are passing, the more our confidence in the test suite decreases. Maybe our tests are not that good. Maybe they are not effective. So, and then we also have something else. If we are running the tests, we are incurring costs. Because we have to run the tests and they are running on machines and the machines are expensive. And we also have to wait for the tests to finish before we can move on with our life. And then we also created those tests and we are maintaining those tests. So we have a lot of costs that are actually associated with those tests. And if they are associated, then probably we are missing the point. So if all tests are always passing and we could actually remove them because they're anyway always passing, then somehow our tests are missing the point. So the good thing is that this is not what happened at Microsoft, and probably it's not what happened at your company. So there were a lot of tests passing, but there were also tests failing. And so how do we feel about this? Probably we feel better. We are like, yeah, some tests are failing, which is a good thing, right? And I actually think that this somehow reflects also why people are always arguing whether or not to test. And when I asked this very fundamental question, why do you test? Some people, I think, thought I was criticizing testing. So they were a little bit defensive. They were, well, do you want to be in a plane that crashes? But that's not what I said. I just asked, why do you test? And but I think sometimes we have to argue that testing is good because it's hard to have some measurements, right? So all tests are passing is not a good thing. Some tests are failing. Is that good? So we know that we cannot test quality in our system. And we know that if the tests are all green, this doesn't mean that we are defect free, right? So we cannot prove with the test suite that our system has no problems, no mistakes, no defects, no errors, right? And so I think this is where we are a little bit struggling as a testing community, where how do we measure the effectiveness of our tests? How do we know its worth? And so we were thinking about this, and we were thinking about in terms of costs and value. So when does it make sense to test? Well, so we have costs and we have value with a test. And so if the value is higher than the cost, then probably we should test, right? This is a good investment for us. And if the costs are higher than the value, then we should probably not test. And so going back to this state that we saw when we were talking with developers, in this project we were talking with developers a lot, we were talking with testers, we were looking at their tests, we were asking them, so what's actually happening here, how does that work? And so we were looking at that and we tried to find out what's actually happening. And so there were some of those tests were good, right? I mean, good, they were bad, they were failing, but that's good, right? So we looked and we watched them and we observed them and we were talking with them, what happens now? And so what they're doing is they're inspecting the test failures, which again is a cost. So apparently we didn't have all the costs. Inspection time for test failures was very expensive. We saw that people sometimes sit quite a long time to understand what's actually going on here in that test. What's actually wrong? What's going on? And sometimes we found out that engineers look like this. Wow, what's happening here? So they are sitting there investigating and suddenly they find out there's no error. The test was failing, yes, but there is no defect. They cannot make out a defect. And sometimes it's because it's hard to reproduce, and sometimes it's because the test is wrong. It's just the test is wrong. Maybe there are some thresholds that should be adjusted, or maybe there's some network that wasn't there, some third party. And the more complex our systems get, the more often those things happen. And we said, well, these are flaky tests. Flaky tests. And this is not a very scientific definition, but what is a flaky test? Well, it's a test that sometimes fails, but without detecting a defect. And it's a test that maybe you run it 3 times in a row and then you take the average of the outcomes, or the majority, of the outcomes. yeah, so there are different things. People talk about flaky tests in different ways, but yeah, it happened. We saw it happen. And now you say, well, but that's not a real problem, because this just means you have shitty test suite. So are flaky tests a problem? Well, they definitely happened in our systems, and they're happening in several systems. So there are articles written about it for example, for GitLab and GitHub and all these CI, CD. They even have mechanisms for rerunning flaky tests. They have like guidelines what you should do with them, you know. And so yeah, flaky tests are happening. And I want to show another study, for example, that was called Understanding Flaky Tests. And so they investigated, because I want to show something outside of Microsoft as well, right? So they investigated in an open source project, tests were even, you know, marked as flaky tests. And so then they talked to the developers and asked them, so how often is this actually happening? And almost 60% said, well, at least every month. And 78%, so almost 80% said, well, this is a serious or a moderate problem. And 77% said, flaky tests are hard to reproduce. They are hard to investigate. It's time consuming. So yeah, when all of that is a pure problem about the test, it only represents a cost. So we learned something more about our software system. So then we wanted to still understand more what's actually going on here with those product teams. And so we tried to understand how their development agility and how their testing practices actually work. And so very simple thing, very simple starting point was, well, you make a code change and then you run your test suite, and then you make another code change and you run your test suite. And if we think about code velocity, and there are many, many metrics and many ways to measure that, we measured it in a way that, well, if you're making this code change, then you have to run your test suite, and only then you can make another code change. So the code velocity would be really from having this code change to being able to make another code change. So including the test suite, you're somehow waiting for the tests to pass. And now this very linear thing, you could imagine if you're alone, it's just you that's working on your local computer. But what actually happens is that there are 10,000 developers for Windows and a couple of thousand for Office. And so there are more people working. And so they are working in, for example, in a structure. And this now, for example, is for distributed versioning control systems, repository systems, where you have a feature branch and the master branch. So those are two copies, sort of the software system. One is local. You're making your changes and you're making your code changes. You're running the test suite. And then you're merging that with a shared code base, right? You're merging your changes into there. And then you have to run the test suite again to see, well, if I'm merging with the other changes that other developers had, is it still okay? And even if you don't work with Git, for example, very similar things happen for centralized version control system, and except that the feature branch would not be versioned, right? So it would be your local copy, and then you're merging it into that central repository. But still, you would probably run your test suite on your local machine and then the test suite on the master branch as well. And so for Windows, for example, the branching structure is even more, is larger, is deeper, right? So you're having 10,000 developers working together, let's say in 100 teams to each 100 developers. And then you would have the teams work on or the person or smaller teams work on feature branches, but then integrate and have integration branches where all the work from one team is. And then you're merging that to another integration branch where the work from another team comes in, right? And so you can imagine that on a day, a lot of changes are happening there and a lot of merges happening there. And on each of the levels that you're merging those together, the different changes, you're running the test suite again. And so there's a lot of repetition of the testing, but it's on one hand necessary, but it's a lot of testing. And the code velocity, as you can see, is longer and longer. It takes longer that you know, well, this code change actually hit the master. This is not production, but it's the master branch. So it's somehow sort of the final or stable version of your system, right? And so let's recap. When we looked and investigated how people are testing and why are they testing and how does it all work, we saw that, well, testing those large-scale systems really took a lot of time, and it was slowing down the release cycles. What we also saw is that some of the tests created false alarms, and we saw that some of the tests are more effective than the others. And so there were rumors about everything. People were like, oh, we could just not test, or, they are not that effective. Others were, oh, it's really important. But there are no hard numbers. And so what we wanted to do is to have those hard numbers. So our idea was, can we test less? Is that possible? And so our idea was that maybe we are just skipping some of the tests on a certain integration branch, for example. But what would happen? And there are a lot of approaches for test case reduction. Traditional ones, for example, look at test coverage. So, for example, which part of the system has been changed and which parts of the test are covering those changes. Or how long are tests taking. So you would only run the long running tests during the night and not during the day. Maybe it's depending on the test. So you have unit tests that you have locally, and then you have integration tests that you have on the integration branches. And then you have this end-to-end test, for example, only at a specific time or day or, for a specific change. There are many, many variations. But what we wanted to do is we didn't want to use any of those. We really wanted to have this cost model and this idea of how effective is a test. And if it's very effective, we would do it. And if the cost of running it, if it makes sense to run it, if the value of the test is higher than the cost of running the test, then we run it. Otherwise, we don't. But how can we measure that? How can we measure the value of a test? We talked a lot about it, and we had these very vague ideas. But what's really the value of a test? And there are many ways you can estimate the value. We wanted to estimate the value based on the likelihood of the test finding a defect. And so again, let's think about the costs. Those seemed very simple. So we had the machine costs. We knew which tests were running on which machines. We knew how much 1 minute of this machine costs, for example. We knew the time of the machine, so we could calculate that. And we also saw that people are investigating those test failures, and so we sat with the teams and we tried to really find out how long is that actually taking, how long, and can we say that for a specific test it takes long, or a test suite and things like that. So we're getting numbers for this inspection time as well. It was intertwined, so we had to dig a little bit around, but there were numbers that we could actually put on that. But how should we put a number, a dollar sign, on finding a defect? How much is that worth? Is it the same for every defect? Is it different? And so I want to take you back a little bit to how this development actually looks like. So if we, for example, imagine Windows, and we would not run, for example, this test suite or one test, and it would have found a bug, a defect on that level, what would happen if we find it later? How much would that cost, right? And so what we saw is that because and this is really important, we are not looking at production costs, right? A production defect. So defects are not slipping into production because we have like a safety net that we always run the test suite before even, giving it into production. This was really development costs. So if you find a defect during development, does it make sense? Or does it make a difference between finding it now and finding it in 2 days or in 4 days? And so when we were talking with the engineers, we found out that yes, it made a difference, because the higher up the test fails and the more different code changes have been merged into the code base, the harder it is to have actually a root detection, so root cause analysis for the test. And so as I said, it's important, these are pre-production defects. They are not defects in production. We are trying to understand the cost of a defect when it slips through during development. But we saw they are different. The costs really depend on how many people are affected by this escaped defect and how long is this defect undetected. And so the higher it actually slips through from the branching structure, the more people will be affected by that. And it's also harder, as I said, to detect where it's coming from. So we then reformulated our hypothesis or our idea, what we want to measure. We don't want to measure the value, but we said, well, let's say if the cost of running a test is higher than the cost of skipping a test, because this is something that we could put a value to, then the test is skipped, right? So as I said, our goal was to decrease the development and testing costs, but without sacrificing product quality. So one of the requirements that we had was that a test at least runs once. So every test has to run at least once before the change can hit master. And so we classified the tests into different buckets. We said, well, there can be tests that have a very low cost and they have a very good value. Those are greens. Those are the ones that we really like. Then we can have tests that have a low cost, but they have a low value as well. They don't find so many defects. We can have tests that have a high cost and a low value. And some of those that we really don't know, so they have a high cost and an unknown value. And what we want to do is we want to run more of those low cost, good value tests and less of all the others. And so this is a cost function, and don't be scared. There's a paper out where you can really, if you're interested in that, look through everything in detail and, with your own pace. I put it there just to make it complete, but I won't go very deep into it. So the important thing is here that we had a cost function. We had to come up with really something that would give us a value. We don't want to say, oh, we estimate it's a good or a bad test. We don't want to sit and look through the test and, make a feeling, a decision based on our gut feeling. We wanted to have a cost function that gives us a value, a concrete value, and another value, and then we can decide whether or not something is higher or lower. And so this is what we did. We had on one hand this cost for execution, where we had the machine cost for running the test. This was fairly straightforward to get. And then the cost of inspecting false positives times the likelihood, the probability of this test of giving a false alarm. And then we had the cost of skipping a test, and we were saying, well, the cost of skipping a test is the probability of this particular test to find an escape defect, right? Find a defect, so this would be an escape defect, times the duration of the delay, so how long are we not finding it, how often is it slipping through, right? And the number times the number of engineers that will be affected. And we knew how many engineers are under a certain development branch. And so what I want to go more deeper into is how this algorithm actually worked. So you can imagine that you're having those test executions. And then the first step, we just run the test executions like we always did, right? So they're running and then they're green and they're failing. And then we get information from each one of those. So we record the test performance. And for each of the tests, we know the test name. And then we were also knowing the branch. And we knew a lot of other things that I didn't put into there. But we knew, for example, this is this configuration of the machine, right? Because these test execution profiles, what we saw when we analyzed a lot of those data is that tests behaved very different for different configurations of the system. Let's say one is an x86 and the other is a 64-bit machine, right? The test could behave very differently. And so for all those configuration, we made a package. So test per branch, per configuration. And then we also recorded the execution time, so how long does it take, and when it finds a defect and when it reports a false positive. And so we did that for each of the tests. And then at one point when we saw, well, there was a threshold, now we are, we think we know enough about this test, we started to enable the cost function. And so then it was looking at the costs, which were based on the time, but also the probability of finding a defect. Maybe the test found one defect every 100 times that it was run, sort of, right, from an average. Or maybe it was 500 times. It was around something like that. So then we could put those numbers into our two cost functions that we had there, and it would spit out whether or not we should skip this test or not. And then we would feed that back into our test record performance. And once in a while, for example, if a test would be skipped for a long time, we would reactivate it as well to just get more information about this test again. And so somehow the system was self-adapting. And what we did then with this, so this was the design of the system. And what we did a simulation. So we took past executions, so we knew the outcome. We knew when it was inspected, we knew whether or not it was a false alarm, we knew how long it took and things like that. And we were replaying everything. And we made our decision, so our model was making our decision. And because we had this decision, which was then the alternative variation of it, we could compare that with what actually happened. And so then we could calculate how much our system would have saved or improved or maybe worsen, right, the test performance and the development execution time. So the results, so we have Windows, we run it on Office and Dynamics, and for different time frames. So for Windows, it's almost 11 months, for Dynamics, it's a year, and for Office, it was a shorter period, it was 3 months. And so we took those test execution, and then, for example, if something slipped through, we could see whether when would we test it, how much time would go by, and we could calculate those costs. And so what we saw is that from a relative improvement perspective, we could skip 40% of the test execution for Windows. And we could also decrease the test time by almost by 40%, right? The test result inspection, we could decrease by 33%. And because Windows is a very deep branched system, which is different from the other two, there were not so many escaped defects, right? There were only 2.0% defects that actually escaped to a different level. They never went into production, right? But they escaped to a different level. And so in total, when we calculated that with our estimates and with our numbers that we had, we could improve or we could save around $1,600,000. For Office, the number is smaller. We could save around $100,000, but it's only 3 months, right? So it's a smaller period. And the test execution, we could save around 34%. For the test time, around 40%. And for the test inspection time, 21%. And then we also run it on Dynamics, which is another system. We could save around 2 million of test execution money, right? And that was 50% of the test executions were skipped. 47% of the test time was skipped. And we had the largest amount of escaped defects. So a lot of defects were actually slipping through to a different level or were detected later. So it's around 13% of the defects were detected later. But still, from our cost level perspective, this was way less money than what we had actually from the test result inspection. So as you can see here, we had almost 2 million in test result inspections, and those are the false positives, right, that you would actually inspect. And we could save that. So even though there were 30% of defects coming up to a later time, we still had a positive, very positive improvement here. Yeah, so I hope you could take something away. Thank you very much for listening to my talk. If you want to reach me, just write hi@michaelagreiler.com or reach me on Twitter. And yeah, so thank you so much for listening to my talk, and it's time for question, I think.